Hey guys, this is the video key of yesterday's little quick quiz. So number one, the first two classes of a frequency distribution are 0, 9 and 10, 19. So you might imagine that you had a frequency distribution with two classes, one over the other. Might be a better way to imagine it. And let's say we had a frequency of 3 in the first class, 6 in the second class. Important thing to remember with class widths is they don't go from the lower class limit to the upper class limit in a single class. You have to think of lower class limit to lower class limit, one class to the next. Or you can think of it as the upper class limit to the upper class limit. You can even think midpoint to midpoint. Any way you slice it, it's 0 to 10, which is a class width of 10. It's 9 to 19. It's also a class width of 10. 4.5 and 14.5 would be the midpoints, and those have a class width of 10. So 10 is the answer to number one, class width for a frequency distribution. First two classes of a frequency distribution are 0, 9, and 10, 19 again. What is the class midpoint of the second class? Well, the second class is the greater numbers than the first class, so 10 to 19 is the second class, and we just want the midpoint of these two numbers, so we find the average essentially. So 10 plus 19 divided by 2 is 29 divided by 2, and 29 divided by 2 is 14.5. Or you can just think of halfway between 10 and 19. 10 to 19 is 9, so half of 9 is 4.5. Either add 4.5 to 10 or subtract 4.5 from 19. Number three, can the original 27 values of a data set be identified knowing that 27 is the frequency for the class 0 to 9? So last one here on a frequency distribution. Again, if you have this class and you know that 27 is the number of data points that fall between 0 and 9, in other words, the frequency of the class 0 to 9, we can't get any of those data points exactly. We only know that they are between 0 and 9. We don't know their exact value, so no, we cannot get the original 27 values. In fact, we can't even get one of them for sure. And that's a drawback of a frequency distribution, is that you don't have any of the individual data points. You simply have the number of data values that fall between a certain range of numbers, which we call a class. Okay, moving on to number four. True or false, when a die is rolled 600 times, each of the 6 possible outcomes occurs about 100 times, as we normally expect. Well, that part's true. The second part is not. So the frequency distribution summarizing the results is an example of a normal distribution. Well, I'm going to draw a histogram of the results, which a histogram is essentially the visual representation or the graphical representation of a frequency distribution. So we have ones, twos, sorry, it's really not much space to write here. But imagine those are the 6 possible outcomes when you roll a die. And if you do it 600 times, you're going to get about 100 ones, 100 twos, 100 threes, fours, fives, and sixes. Most likely not exactly 100 of each. But the more rolls you do, the closer and closer they will get to equal. Problem is, this is not a normal distribution. A normal distribution resembles the bell curve. This is called a uniform distribution. When the heights of the boxes in a histogram or the data is spread evenly and equally across, then we have a uniform distribution, not a normal distribution. All right, when you're analyzing a data set, oops, sorry for the typo there, that should say data. It's important to investigate the center. Yep, we want to know about the mean and the median. The distribution, What's the shape? Do we have a lot of data on one side? Do we have it spread out? Outliers. Outliers are important. They can change the mean by quite a bit and other things. Changing patterns of data over time. Yep, all good. The last thing we're missing here is the variation or spread of the data. You can have two data sets with the same mean. One, they're all clustered around the mean, and the other, they're spread out far from the mean, but balancing each other on both sides. Those are very different data sets. So variation is the fifth important consideration. 6 is a stem plot key, essentially. This is the stem here, the 5. Whoops, bad arrow. 2, 2, and 9 are the leaves. And that means that the 5 is the tens, and the 2, and the 9 are the ones. So we have a 52, another 52, and a 59. That's how a stem and leaf plot is structured. Number 7, it's important to recognize what sort of visual representation you're going to do for a data set. So if our data is shoe sizes and heights of 30 randomly selected students, well, we have two variables that we are pairing. So if we have one person and we pair their shoe size to their height, then we call that a matched pair data set. And the best one for that is a scatter plot. And a scatter plot, you've done them before. We might have height on the y-axis, shoe size on the x-axis, and we're most likely going to get a scatter plot where the height increases as the shoe size increases. Number 8, true or false, a histogram and a relative frequency histogram constructed from the same data always have the same basic shape, but the vertical scales are different. That is true. A regular old histogram resembles a box plot, but what's on the y-axis are the actual values or the number of occurrences of each range. Comes from a frequency distribution, and a relative frequency histogram would just have the percentages on the y-axis, but each bar would be relatively the same compared to the other bars. So they would look the same, they would just have different y-axes. Number 9, what characteristic of a data set can be better understood by constructing a histogram? Histograms are great for showing the shape of the distribution. How are we looking here? We got a lot of data to the left, and we got a few data points as we move to the right. Maybe those are outliers. Those are going to draw the mean up. Or maybe we have a little bit of data and it gathers some steam here as we get to the middle, and we have more of a normal distribution, a little more consistency. And so the histogram is great for showing the shape, or the sometimes called the distribution. And finally, number 10, which graph is best for showing the relative importance of these defect categories for light bulbs? We have broken glass, broken filament, broken seal, incorrect wattage label, or those are just categories of defects. So the best one here for showing the categories of defects would be a Pareto chart. And a Pareto chart is nothing more than a bar graph with the highest frequency occurrence on the left and then decreasing in value. So it would always go highest to lowest. In this case, you might have broken glass is the most, broken filament second most, broken seal, incorrect wattage would be the fourth most. And you would, because this is categorical data, you would label those things on the x-axis. And each bar represents the frequency of that category. Hope this helps, guys. Sorry it's a little long. We'll talk to you soon.